This right here is an old power drill, but it's still modern technology, and we're going to take a look at all the pieces that live inside of it, like these gears, sun and ring gears, etc. Hi everybody, I'm David Malloway. I'm a robotics engineer. I'd like to use this video to give you guys a walkthrough of the elements that live inside some of these power tools. Well, pretty much all of them. Get you familiar with some of the components and then understand what is the value of the individual component outside of when it lives inside of the machine, because there's a few elements that you could actually retrieve them and reuse them in other ways, or just knowing about the components inside of a device can help you understand the value of a tool, whether it's on sale or whether it's a really nice brand or a cheaper brand, to just read the specifications, and then you have a sense of how the value of that tool compares with another. And then in the context of Open Lab, this open source lab that I'm trying to document further and further so that we have a template mechatronics prototyping lab space that lives online, that people can retrieve best practices and exchange new ideas to fill out this new industry called mechatronics engineering. These components are fairly central to that, so it's worth talking through it. Okay, a friend of mine dropped off this broken power drill, but it's only broken in one way, and there are several modules. So I decided we'll tear it apart, look inside, share that with the audience, so that if you've never taken one apart, then you can know what lives inside of there. And it's only a few modules. So the way that I see these devices is in terms of a set of modules, and each one can be a higher or lower quality. But this is a fairly standard size of a well-made brushed motor, brushed style power driver. Some people call it a drill, but this is a drill driver. So what lives inside of here is, if you were to open it up, you'd find a drill in the back. You'd find a gear train here in the middle. And this gear train is obviously disassembled. As soon as I unscrewed this part, it starts falling apart, and that's not easy to reassemble. So this is just, for the visual aid. You have one simple spur gear that's steel, and these are hardened steels. This is a really nice steel that all of these are made of, and that's standard. If you spend more than $50 on any drill device, then you're going to get something like that with the modern brands. And then this outputs to the gear train, and you can select two different gear ratios. So you've got a low and high speed. I think there will be a familiar button. Everyone has maybe seen this that works with those drills. Usually the one that comes with a chuck will have its own mechanical gear selector. One's low speed, high torque. Two is high speed and lower torque. That doesn't do this has no impact on the power being sent to the DC motor that goes out to the shaft, to the drivetrain, if you will. That is a pure mechanical selector. It would change the gear ratio within this gearbox. Okay, and then you have the trigger module that I've already ripped out. Trigger module is here, and that's the special component for today, where this is essentially an H-bridge and a little bit of extra circuitry. I'll come back to this. So the trigger module lives in there, and the trigger module lives in between the battery at the base and the DC motor up here. And it is sending a lower, medium, or higher, a selectable level of power up to this motor. And it does that in the form of voltage. You have an 18-volt battery. There's a circuit here. Main point is the tabs that reach into the battery when you plug a battery in. So you have access to your full 18 volts on a fully charged battery, maybe 20.5 volts, and a lot of amps available, but 0 amps are sent until you pull this trigger, and then it starts to raise the voltage that's reaching these two wires, therefore raising the voltage to the motor, available to the motor. And since this has essentially some nominal resistance, then more and more voltage is going to make this consume more and more current and produce more and more power in the form of rotation. Oh, okay, and so it's really, that's the same for any of the different brands. We can, for example, compare this one. It's going to be almost exactly the same. And so now, as you get familiar and you start to work with these, you can start to say, oh, well, I like this style of the clutch in here, or I like this, I want to see a brushless motor that reaches this many RPMs. You can start to have your preferences for each of the modules, and that preference turns into, then when you go shopping, then you can get the value. If you have the most expensive, fanciest tool, but it doesn't match your preferences for the jobs you need to do, then of course you're losing out on value. So the thing to note about this one, you notice it's a little bit smaller and it's brushless, I believe. I upgraded a few years back, and that means the same given motor size can usually crank out a higher power. But higher power, of course, that also means you're draining the battery faster. So again, your preferences. Also, the brushless maybe at times, I think at the very best, it's capable of a higher efficiency than the DC motors. So running this at mid power or full power all the way through the life of the battery is going to live longer than the equivalent model that's using the brushed motor. And it may also have a higher peak torque. Back to the anatomy. Regarding what was broken in this assembly, in this machine, what was broken when it reached my hands was something in this base circuit that communicates or interacts with the battery that you plug in. And so the issue was just water damage. It was left out in the rain or something like that. And if you encounter water damage for a tool, any tool like this stuff, then it is likely that your chuck assembly will survive, your gear train will survive. It's very likely that your motor will survive just fine because these tend to expel water unless it was sitting and able to corrode and have contacts kind of messed up, then these DC motors usually can survive. And then the the more susceptible components would be this guy and your trigger assembly. And so to test whether this is still working, first we just need to know what it does. If I want to test if this is still working, I have to offer power to it and have basically the whole drill assembly ready. And then how do I communicate that? Well, if you look at it as a chain of elements, then you can start going from the bottom, removing elements, and if you can offer a signal or a power, etc., to the chain after that, and that subsystem works, or that set of modules works, then you know that the problem lies before that point. So I yanked this out, and then I hooked up power directly to this, which really only has 4 important terminals. So the way that we know what this even does is a set of, I guess, clues. So you can see M1 and M2. Those 2 terminals were sent out to the motor. So this is motor 1 and motor 2. And you have a, let's see, battery plus and battery minus. And those, I mean, I think they were actually colored wires when it was connected in the machine. So the color helps, but also plus and minus helps. And so why do we have motors? Why is there not a positive and negative for the motor? That's because it is reversible. So when you're using the machine, then above the trigger, there's this button that can click and it moves the white lever. This would be off on most drills. This is backwards, and this is forwards, or the opposite of that. But we do know that this is going to control the direction of our motor output. And therefore, there shouldn't be a positive and negative for the motor because you can switch them. There must be a function inside of here that digitally indicates electronically controls the path of the current and the voltage. And so I haven't even broken this open because we got it working already and I don't want to tamper with it any further. Then we just had one more smaller contact. By the way, the size of the tabs and the size of the solder and the wires gives you an idea of how much current is going through a terminal. And this one was smaller. This is the original wire. And it says L, and so certainly this was sent out to the light, the LED light, which a lot of these tools will have a light, like in this case, there's one down here. A lot of the tools have a light, and that's nice. It lets you know, for instance, before you pull the trigger all the way, you pull it just a little bit, and there's a sensor in here that says we have some amount of trigger pull, and then it'll turn on the light. Okay, that's information for the user. It's pretty useful. So I think I tested that, and it was with 18 volts coming into the module, we only had like, I think 8 volts going out here. 8 positive. You could measure this with a positive probe on a multimeter compared with that ground. You treat this as ground, and you'll see a positive 8 or 6, something like that around here. And you'll notice if you power this up and you have nothing connected out there, then you can get that to modulate by, you can turn it off entirely. When that's off, you can't get it to light up. When it's forward or reverse, then that voltage turns on. And then you start to understand how the module itself works. Okay, so DC motors, because we know this one is a DC motor, if it didn't say it on the specifications or in the manual, then you can understand by, if you can find brushes, and you can measure continuity. You could talk with ChatGPT and then ask, oh, how can I probe this motor to discover whether it's DC or AC? That's a pretty short and quick test, but I'm familiar at this stage just by looking at it. And by the way, there's no gearbox inside of this motor housing. I can map this whole machine over to our Scuttle robot. So the motor plus the gearbox is equivalent to our DC motor and gearbox. So this, you could interchange these. You could use that motor controller to send variable current to this very motor. I could literally solder these 2 wires that come out of our motor here over to that and plug and control my motor with that device, or I could use my DC motor control module here, which is called a dual H bridge, one H bridge for one motor. It can send current that has a variable amount, just like I mentioned, from a low voltage to a high voltage, and it can also invert that current so that your motor is going backwards. Only difference between this and that module is that one is receiving its inputs from a sensor that's probably embedded on the circuit board and attached to that lever, that trigger lever, and ours is receiving its signal from these signal wires. 2 wires for each motor and 1 ground. So you could remove everything and you'd have these 4 terminals, 2 powering to go in two that power and go out to the motor. So we send it from the battery and spend it on this motor driver. Or if you isolate the motor driver as a system, you're sending it out to the motor and spending it at the motor. And then, so this is a DC gear motor. We call it a gear motor because in that gray, larger diameter housing, it's reducing the speed of the DC motor. Most DC motors around this size range are going to spin up to maybe 10,000 RPMs or many, many RPMs, and it's more than you want. It's a higher speed and a lower torque than you usually want for most common appliances, whether that's a blender or a drill or the tool that's doing work on the order of power as a human could do work, filing, a turning, a twisting, that these motors, to achieve that amount of power, the speed is usually higher. And it's not common to find a motor that can do a slower RPM and a high torque. So we start with a motor that's spinning fast and we slow it down to increase its torque. And that's just common across many, many appliances. Okay, now I have these two rotating tools, rotary tools, or this one may be referred to as a cutout tool, to compare them in terms of engineering value. This is what I see when I'm looking at these. Both of them are capable of carrying these types of, it's a 1/8 or 3 millimeter shaft tools, like these gorgeous little carbide burr tools. Like this is one of my favorite filing instruments or cutting instruments that can cut steel, and there's not a lot of other tools in the lab that can do small filing, carefully controlled cutting of hard materials like steel. And so then when I do a job like that, I have access to this Dremel, which is one value is that we can control the speed in a variable amount. What I think is that we have a fixed 4 volts, 3.7 volts, and there's a circuit board in here that basically listens to the switches coming in, and we get 5 discrete power levels, including 0. Okay, so now we have control over the rotating velocity. That is desirable for any time when I'm using this tool. I also would like to have the ability to control its speed. It very much makes an impact on heat buildup and the effectiveness overall. These are not all designed to go at the same speed, and I want a very high speed on the burr tools on steel, and maybe half of that, say, if I want 25,000 RPMs on this on steel, and I may only want 10,000 RPMs when I'm shaping plastic, and then maybe less than that when I'm just drilling a hole. So that is one of the its value in terms of engineering and work, and it's also a cost in terms of the tool. And so you have my most frequent complaint with this tool is that I'm wanting more torque. So I'm cutting a hard material, or I'm using one of the larger bits here, then it's taking more energy, more power to do the work, and I can run out of torque. When you're going at a high speed, if you press hard against the surface, then it's going to stall. A little red light will blink and it just stops. And I have to bring it all the way back down to 0 and spool it up again. Versus this larger, it's a larger battery and it's a larger motor with a much bigger torque, but I can still achieve that same RPM. So the value here is I'm going to use this for heavier jobs that are going to last longer without the battery dying, or what I just simply cannot achieve the work that I want to do with this smaller torque. However, this one is just an on-off tool. You've got one switch, and it's a brushed motor as well, so it could this brushed motor could have a controller that has a variable speed available, but it doesn't. That would cost more to make the tool, and maybe the price in the store would be higher. And they do make variations of it. It's essentially the same thing when you look at, I'll grab it. When you look at this tool, I forget what they call it, but now this one has a trigger pull with a variable level of, you can control the speed with your finger, and it has the same ingredients as this one, but more flexibility and speed. And that's what I wish that I had on this device. So we can achieve that if you wanted to hook this up before, after the battery and before you go into the machine. Okay, so we have this 3D printed module that's a dummy for a battery. It pretends to be a battery, and it has these two terminals plugged in where the battery would be. And we have some chaos of wires, but all you need to know is the wires map back to this other battery. So we have 18 volts at most. We could send, using this device, we'll send at most the full voltage of this battery to the machine. And the machine, that's what the machine is rated to handle anyway. So we're not going to hurt anything. We're just going to send, we might hurt it if we go in reverse, which this doesn't have a reverse switch. So we're going to keep it in one direction. Hopefully I still had it in the same direction as before. I forgot. Anyway, we have 18 volts coming here. I've powered this on. I've powered this one from the off to the on position. Now, normally this tool would be running full speed, going for 28,000 RPM minus whatever the battery has been drained to. And instead, we're just going to get however much I pull the trigger. So this is maybe the minimum. I'm limiting that battery's voltage by the amount I'm asking for with the trigger pull, and then it goes straight to the motor in here. There's very little circuitry in this machine that controls it, so we're able to do this. And then we can go medium. So I can listen to the pitch of that motor turning when I go full trigger pull, and that sounds just like it sounds when I have this battery hooked directly into the tool. Okay, just for funsies, we can also operate this big treadmill motor with the same battery, 18 volts, and the same power module. And then basically we have the 18 volts goes into the power module as before, and then the two wires going out are going into this power distribution block. These are DIN terminals. They're easy to hook up and replace and swap and change. And then the positive and negative jump onto the next cord. This is all 16 gauge wire. And then it goes into the base of this big motor. It ties in where the old circuit was tied in on the treadmill. And it has a big, heavy mass, a flywheel, if you will, on this. And we can control that as well. So I'm going to leave it in the same direction as before, and then I'm going to press just a little bit on the terminal, on the trigger, and you can see we get a slow rotation. This is a beautiful motor, by the way. It has such a nice linear response from a low speed to a high speed, and that's something that I expect. When I take apart a treadmill machine, I already know, well, these are, they have settings to go gradually from a low speed to a high speed. So that motor should be built such that it can accept a wide range of voltages if it's DC. And so we can go further. Oh no, that's full power. So this motor is rated to go up to 120 volts of DC, which is really high compared to most appliances. And if I let off the trigger, it slows down, but then if I let all the way off, it kind of jerks. I think because this has a braking function of some sort. Okay, and then we can also reverse this direction and then hit it again, and we can go the other way. What I learned about this trigger module is that it doesn't have a lot of gradation, I don't know, a lot of smooth steps between 0 power and full power. There are at least 3 discrete settings that I can find, and I think there's a somewhat of a continuous range down near the lower side of the trigger pull. So that's full, and if I release it quickly, I won't do this a lot, but just once, you get that, you can see the inertia jump and pull this whole assembly back the other way. And we power off, and we can simply take the screwdriver and remove these wires from the screw terminals. Okay, now I have those available, and I don't want to turn this back on while those wires are exposed. These are simply ferrules that I used in lots of projects, and I think I've shown before. They are crimped on, and that you just need to select the size that matches your wires. I use a lot of 18 gauge wire, that's this size, and then for a heavier machine like this, I'm using 16. Essentially, you can choose by just matching the size of the copper that you're finding in the machine that you're dismantling. Okay, so if you wanted to reproduce this project that I just did, I'll walk through in this section just the tools that are required, because there aren't that many tools and there aren't that many supplies in order to do this, and then maybe the audience will gain familiarity. This is the same equipment that we use for the robotics projects, the same supplies that we use for many other projects, and this is why if this appears to be along your path of project space, then I would recommend everything you see here has been tested, benchmarked, and compared with other similar options over at least 5 years. Okay, to disassemble the plastic housing of this drill driver, all it took was a Phillips 1 screwdriver, and those were ordinary Phillips screws, but they're just a little bit deep set, recessed into the plastic. And so this is you want a narrow, a convenient narrow screwdriver for that, that's at least got an inch of length to it. The alternatives that we use all the time are this type of bit set based screwdrivers. They have all these collections of bits that come with them, but they're a maybe on whether they will reach or not. Then to cut wires free, then we're using a steel flush cutter that lives here on the bench top. We almost don't even need to leave this bench top in order to do the project. The flush cutters, this specific one, it's not a stamped steel. It's actually either forged or cast steel shape, and then it's actually ground, so you have that very fine precision point. But you want to, when you're cutting larger things like this diameter, then you want to grab all the way down so that you're not damaging the tip. That's the best odds. You really won't damage cutting copper or tin with steel. You should be fine. Then moving the solder, removing the solder from, let's say on here, on this trigger mechanism, we've got to heat up those solder points on the previous wires, and you just lift them off. It's that easy. And you need at least probably 40 watts on your soldering iron. And so the most soldering irons will do it, but I would say if you have one of these, $10 units or thing from the dollar store, it may or may not be hot enough to really get you going. And then I cranked this up to a very high temperature because I believe those initial terminals with the solder that was on the circuit board from the factory, it was lead free, And there are certain certifications. So most of the store-bought circuits you'll find with lead-free solder, it's a lot harder to work with, and it has a higher melting point. So I would add a little bit of this leaded solder. It's heavily leaded with I think 40%. Anyway, that's easy to Google and learn more about the types. But I added a little bit of my own solder that mixes with the solder that's on the board, and it becomes easier for the whole little puddle, the whole joint, to become liquid and then come free. I did end up using, you could get away without it, but I did end up using the solder sucker, which is simply a pump. It has this volume in the body that turns to a vacuum. When you press this button, then it's going to lift that liquid solder off of a joint once you've melted it and you have it nice and wet and melted. Then you reach this up to the tip, and then you just press that button and it will suck up a big glob of the solder. Maybe half of it will be gone and the rest is easy to work with. Then I'm always using my favorite wires that are already paired. That reduces the messes that you work with, the craziness of the wires when you're prototyping things. This is silicone, and it has fine strands. So in most projects, the fine strands makes it more flexible and more easy to work with. And instead of having frayed, messy tips, we add these ferrules. And the ferrule crimper looks like this, and it's right here at the station. You can get these tools for maybe $15, $20, and they have this these steel little plates that move in and crush the tin alloy sleeve with these ferrules that look like this. 16 gauges like this. You slip that onto the end of the wire and then you crimp it. In order to send power to any of your tools, now people have created a lot of 3D models online where you can build your own terminal dummy. But this one, for the rigid tools, I have a lot of them listed on GrabCAD. So all I did was place the wires into the slots, and I crimped on these spade terminals. These are not exactly ideal. You will have a slightly more limited current that you can send to the tool, but for short term and for testing, this is totally satisfactory. And these would just slide into the prongs that grab a hold of it inside of this housing. Then we have these red and black Anderson terminals that we use on, I use these whenever we're working with 10 amps or larger. So they have a nice conductive terminal inside that gets crimped with a heavier crimper. Anderson is one of the brand names, but now there are many. This device is available probably $15 or $20 as well, and it should last a lifetime. There are replaceable jaws, and in any case, so there are 15, 30, and 45 amp styles of these, going from small to large, that crimp onto the wires, and then those crimped ends of the wire gets slid and snapped into the front of here so that you can see the tips of the terminals there. And then, so I treat these connections, this is semi-permanent. This is more costly, probably $1 or $1.50 worth of equipment on the end of this wire. And so that's what I build when I'm sure I want to keep it in this format. And before I'm sure, then I'm just using those ferrules, like you see here, to get something quickly put together. And I can always snip these clean and add this later if I decide to keep it. And the last bit is to temporarily or quickly get wires bridged together. Black goes to black, and you have continuity from left to right on each of these. The wires plug into a hole, and this is, I think, called a Wago. Wago is a brand, Wago style terminals. And so we just have a container full of these on hand. That these get used all the time during prototyping. So I think that's it. The total tools are quite minimal. You can do a whole lot with just a few tools. And what I love about this project is that all of the tools are also ones that serve many, many other projects. There's nothing that was especially needed for this project. So, and also I apologize to Joshua. We have a team member, Joshua, who's a mechatronics engineering recent graduate, and he's working here in this lab. He is totally capable of doing the explanation for the driver breakdown and its electronics, but yeah, I'm working on getting some camera time for them, and we're working out how to work the cameras and microphones and the space with multiple people here in the lab. So I'm looking forward to that. And what else? Okay, very last thing. There was one question, a mystery that was solved for me in the course of dismantling this drill, and that is, what kind of mechanism lives inside of here that allows the slipping clutch, where you'll hear a clanking sound like that, and you can use this, let the clutch slip and have that cranking without damaging this over the life of the tool. And the way that looks is it takes place on this ring where there are little ball bearings that live in the groove, and they jump over the humps on this ring. And so there's an interface inside the gearbox where this is able to slip with respect to the forward set of gears by these balls just jumping over the humps. And I would expect, I didn't look super close, but I would expect that when you adjust the torque on that clutch, you are probably simply adjusting the closeness or the spring pressure of one side of the assembly up against those balls on the other side of the assembly. And so a higher pressure means it's going to be a stronger torque before it slips. And you can hear that heavier clanking, and over here it's a lighter clanking. So that's all, folks. Have a great day. Hope you learned something, and feel free to add any comments if you've got information, if I missed something, or if you have questions that would go along with this topic in a future video.